I left off in the first video, we were talking about determining the asymptotes of this rational function. And in order to find the oblique or the slant asymptote, we have to divide the numerator by the denominator in order to figure out the equation. So I'm going to do some polynomial long division, taking x squared and dividing it by x minus 2. And the first thing I'll look at is, how does x squared divide x? And you would get an answer of x. Multiply that back through and subtract each piece. So subtracting, I get 2x, and I'll divide once more. How does x divide into 2x? And we get 2. And it really doesn't matter what the remainder is. That quotient there is your slant asymptote, is the equation of your slant asymptote. Let's also take a look at intercepts of the function. If I let x equal 0, I'll get 0. So I've got one intercept here at 0, 0. That's my y-intercept. And if I set the function equal to 0, that'll tell me my x-intercepts. And multiplying this denominator here, you'll get 0 equals x squared, which gives me x equals 0, and it turns out that the x-intercept and the y-intercept are one and the same. So we were able to come up with one point that we know is on the graph. We also have two different asymptotes that we know that we can draw. Alright, so let's move on to the first derivative test and see what that can tell us about increasing, decreasing, and local extreme. Alright, so first we have to find our first derivative. And in order to do that here, I need to use the quotient rule. So remember, I'll do low d high minus high d low over low low. And that'll give me x minus 2 times 2x minus x squared times 1, all divided by x minus 2 quantity squared. Let's clean that up. I'll distribute the 2x and I'll combine like terms. And there we have our first derivative. So let's set that first derivative equal to 0 in order to find our critical values. And I do need to set both the denominator and the numerator equal to 0. So I'll do that one at a time. Setting my numerator equal to 0, I've got two critical values at 0 and 4. And setting my denominator equal to 0, I get 1 critical value at x equals 2. Alright, so we've got 0, 2, and 4, which creates 4 different intervals, and we need to test each interval in order to determine its behavior. So because I have so many intervals, I'm just going to make a quick little table. So my first interval goes from negative infinity to 0, and the test value that I'm going to choose there is negative 1. So remember, to determine the sign, I need to take that value and I need to plug it into my first derivative. And it looks like I should get a positive result there. My second interval goes from 0 to 2, and my test value is going to be positive 1. This time I get a negative. Going from 2 to 4, my test value being 3, I come up with a negative value once again. and from 4 to infinity, it changes to positive. So we've got increasing, decreasing, decreasing, increasing. And from that, we want to gather our local min or our local max so that we have more points that we can plot to graph our function. So here we are increasing, and then we change to decreasing, and that creates a maximum at x equals 0. Plug that into the original function in order to get the y coordinate, and we get 0, 0. Here at 4, we're changing again, going from decreasing back to increasing, which creates that local minimum. And that gives me 4, comma 8. And again, I just plugged that 4 into my original function in order to get its y value 8. Okay, we've also got to take a look at our second derivative. So here, when we're taking the second derivative of a rational function, it gets a little bit tricky using that quotient rule. You just have to be really careful about watching every little sign. So I'm going to do that same thing again, low d high minus high d low over low low. And I'm going to do it with my first derivative here, which is also a rational function. So beginning with my denominator, just as it is, I'm going to multiply that by the derivative of my numerator. And from that, I'm going to subtract my numerator multiplied by the derivative of my denominator, which requires a chain rule. All of that is divided by my denominator squared, which raises it to the 4th. Now, you might be tempted to start distributing and combining like terms, and that is something we have to do, but you might also notice here that we have this x minus 2 in every single term, so it's nice to reduce those before you start doing any of that combining. So this whole x minus 2 is going to go away. Here we have x minus 2 squared, and one of them is going to cancel. And here we have x minus 2 to the 4th, and one of those is going to cancel. So now I have x minus 2 times 2x minus 4, and then I'm subtracting 2 times 1, which is just 2, times x squared minus 4x. And in the denominator, I've got x minus 2 cubed. All right, let's get to that multiplication, that distributing and combining of like terms. So here I'll get 2x squared minus 8x plus 8. And then over here I'll also get 2x squared minus 8x. And what I'm going to do is I'm going to subtract it. So I need to remember to subtract each term, change the sign of each term. A lot of things are going to cancel here. The 2x squared minus the 2x squared, those are going to go away. Negative 8x, positive 8x, also going to cancel. That leaves me with a final second derivative of 8 divided by x minus 2 cubed. So remember, the point of that second derivative was to determine if I had any inflection points, and also to figure out our intervals of concavity. So as I set this equal to 0, in my numerator there is no variable, so I'm not going to get a solution there. But in my denominator, 2 is going to be a candidate for an inflection point. I just need to test some values in order to figure out if it is or it isn't. When I did my test values here, I got decreasing to the left of 2 and increasing, concave down, and then concave up. So I got a negative on this side and a positive on this side, and that change means that there is indeed an inflection point at x equals 2. Let's plug that into our original function in order to find out what the corresponding y value is. Now if you go back to your original function, you'll see that we're actually undefined at that value. It's going to be located right on top of our vertical asymptote. So it actually is not going to be an inflection point because it is undefined. Alright, let's put all of this stuff together to create a graph. So first thing I'm going to do on my graph is draw in any asymptotes and plot any points that we've discovered. So if I go back to my original information from f of x, I found out that I had an x-intercept and a y-intercept simultaneously at x equals 0. And I also have a vertical asymptote at x equals 2. And I've got a slant or an oblique asymptote at y equals x plus 2. So I need to graph that as well. It's got a y-intercept of 2 and a slope of 1. And it's not exactly straight, but you get the idea. Alright, in addition to that, we had a local min and a local max. So our local max actually was right here at 0, 0, in the same spot we've got an intercept. And our local min was at 4, 8. So somewhere up here, we've got a minimum. So let's put all the information we have together and figure out how we're going to connect these points and plot this final curve. So in our first derivative test, we had 0, 2, and 4. And we had signs of positive, negative, negative, positive. Let's also take a look simultaneously at our second derivative test and what that told us. And we had negative and positive. So, as I go from negative infinity up to 0, I'm increasing and I'm also concave down. I'm also restricted by this asymptote, so we've got to make sure we follow the line of that asymptote. So increasing and concave down. And then from 0 to 2, I'm decreasing now, and I'm still concave down. And once again restricted by that asymptote. From 2 to 4, I'm going to be decreasing and concave up. So something like that. Decreasing and concave up. And then finally from 4 to infinity, I'm increasing and still concave up. Noticing that I'm restricted by the limits of the asymptote. So that would be an appropriate graph. And when you guys are doing these types of problems, you'll likely have a multiple choice answer. And so you want to look at the location of the asymptotes and the location of these critical points in order to match the correct graph.